Okay, so our next speaker is Daniel de Florian, and he's going to talk about precision QCD at the LHC.
Okay, so I would like to thank, as everybody else, the organizers for this very nice meeting. And I also would like to congratulate Nathan and Rogerio for running this institute for already how many years? 8? Almost 8. In a very successful way. I would say even, at international levels, but particularly considering all the difficulties that we have typically in Latin America, they are doing an amazing job. And it's a very useful tool for the community, so thank you. I hate you. And okay, so I come from a different community. I do QCD, but on the high energy physics side, so basically calculations of cross-sections for the LHC. So it's been very useful to listen to your talks and understand and learn a lot of things. So what I would like to do is to tell you which is the present status of the field in terms of precision QCD calculations for cross-sections at the LHC. Let me try to introduce that a bit. I think it's clear that I can say that the LHC has been incredibly successful. Those are the results for rank 1 at 7 and 8 TeVs. You can see the measurements of many different cross-sections for different final states, cross-sections that span something of the order of 12 orders of magnitudes, an impressive agreement between the experimental results and the theory. And by the way, this is called the dinosaur plot for obvious reasons. But the situation is even nicer if you look at run 2. In run 2, you have the same observables, but not only inclusive. You have the same quantities now accompanied by several sheds, up to 7 sheds. And again, when you look at the comparison between the theory and the data, everything looks fine. Everything looks like a standard model. And even the Higgs boson that was found a few years ago behaves like the standard model Higgs boson. This is also a dinosaur plot, but it's a clear example that when you have more data, it's much more difficult to fit it. Now, of course, we will all agree that there should be physics beyond the standard model for many reasons that I don't need to go through them. That a few years ago we had some theoretical candidates for this new physics, but since nothing was found at the LHC in that direction, no direct evidence of those particles, I think it's pretty fair to say that now the search is basically completely driven by experiments, which is a very interesting situation, actually. And then we're in the situation, of course, that in order to find new physics, we have at least 2 very clear possibilities. One that everyone would like to see is to find a resonance in some invariant mass distribution and then claim that that resonance corresponds to a new particle, something beyond the standard model. In order to do that, you don't need very precise theoretical description because you want to see a real peak, a real resonance in distributions without relying too much on any biases from the theory side. But of course, if you want to do the analysis of that object, then you would need a more accurate theoretical description. That's one possibility. If I would have to bet some money on what is going to happen, I would go into the other direction. We are going more into the direction that we might be able to see new physics in an indirect way, in terms of precision physics, in terms not finding new states or resonances, but probably looking at new interactions in the sense that we might look for small discrepancies, maybe at the tail of a distribution between the standard model results and the experimental data. And certainly for that, we really need precision theoretical calculations because we are looking at something of the order of the percent level. So we need to achieve, in order to do this, something of the order of 1 or a few percent level accuracy, both from the experimental and the theoretical side. And if there is one place where there is a chance to see something, is in the Higgs sector, because the Higgs is the only scalar particle of the theory, it's more likely to behave as a portal to new physics, but also it's the sector where we have the largest uncertainties from the experimental side so far. So there is room for new physics. And just to give you an idea of what people have been looking at for the next 20 years, remember that at some point the LHC will start running on the high luminosity mode. It will accumulate much more data than has reached so far. But that means about 20 more years of running of the machine. So people have been looking at expectations, particularly on the Higgs sector, to see what we might find 20 years from here. And in order to do these projections, what they did was two very simple steps. One was to assume that the experimental uncertainties will scale according to a square root of the luminosity, what you will collect in the future. Things will probably be better than that, but it's a conservative approach. But they have also assumed that the theoretical uncertainties in 20 years will be reduced by a factor of 2, which is not a trivial thing to do. And even after that reduction of a factor of 2, if you see, for instance, that the expectations for the different channels for the production of the Higgs boson or the branching ratios for the decay, you will see that the red line, which is the theoretical expected uncertainty, still dominates over the experimental one. So we really need this factor of 2 of reduction in the theoretical uncertainty, and probably something more than that. And that is not easy to reach at all. And of course, if we are looking for non-resonant BSM physics, it means no new particle observed because it's too heavy, we have to take into account that our standard model is a bit more than what we consider the standard model today. We have to find a way to parameterize these possible deviations with respect to the standard model. And the proper way to do that is by going into an effective field theory Lagrangian, by incorporating, adding to the standard model Lagrangian operators of dimension 6 or larger in order to account for these possible deviations. And when we do calculations now, when we mean precision, I mean precision not only for the standard model, but for the standard model plus the effective field theory. So the outline of my talk is that, basically, after this introduction, I would like to show you which is the state of the art in terms of precision QCD calculations, where actually this P might mean precision perturbative, but also, in the sense of this talk, production of different objects at the standard at the LHC. So I will go a bit through about the Parton distributions, calculations being performed at next to leading order or even higher orders, and then I will provide my conclusions. Now, clear at the LHC, QCD is everywhere, and I would like to remind you that every time we compute a process at the LHC, we rely on this very simple factorization theorem, on the idea that we can write a hadronic cross-section for the production of a system with, say, a large invariant mass, a large transit momentum, where there is a large scale involved, as a convolution between the Parton distributions, the probability of finding a Parton in the proton, times the Partonic cross-section, plus we know that there will be some power corrections that we are happy to assume that they will be very small and we can forget about them. And it's clear that in order to have a precise hadronic cross-section, we need precision from both the non-perturbative and the perturbative part. And of course, everywhere here is implicit or explicit the fact that everything depends on what we call the fundamental QCD parameters, the coupling constant, the masses, and so on. But I saw that after the discussion today, I realized that even though we use the same tools to communities and a very similar language, is not completely exactly the same what we do in the way, particularly how we treat the fundamental QCD parameters. And actually, you are recording that, I shouldn't say it, but probably as you said in our community, we don't treat alpha S and the masses of the quarks as fundamental QCD parameters as you do it. We treat them more as effective parameters, and we put them at the same level of the Parton distributions. And in a way that they are pretty much correlated to the perturbative expansion we use for computing these observables. Let me give you an example. We know the language, leading order, next to leading, and next to leading. But just to give you an idea, when we mean leading order, what we mean is that we do this calculation by using Born-level Parton cross-sections, PDFs, which are obtained from fits of the available data, but this PDF at leading order are obtained from a leading order analysis, meaning by comparing experimental data to theoretical calculations using only Born-level results, and one loop alternative Paris equation for the Parton distributions, and alpha S, and in principle, I should say the same about the quark masses, but the situation there is slightly different. They are obtained from a leading order analysis and evolve with the one loop beta function. From a leading order analysis, I mean that we extract the value of alpha S by doing this comparison between the experiment and the data for a number of processes. At next to leading order, we do the same at one order higher, and next to leading order, the same, and so on. So for us, alpha S is not a single number as it is for you. We are looking for alpha S as the coupling constant of the theory. For us, alpha S is more like an effective parameter which could have different values at different orders. So just to give you an idea of the result for one particular analysis, alpha S at leading order would have this number, at next to leading order this one, at next to leading order this one, and so on. In a sense, I claim that it is a bit effective because we are incorporating into the extraction of alpha S and the Parton distributions effects which are probably of perturbative origin, in terms that we are missing from the lack of higher order calculations. And that's the reason why alpha S at leading order is larger than at next to leading order, because when we do a leading order analysis, we include only the 3-level cross-section, which is typically smaller than the two-loop one, and therefore alpha S will be larger in order to compensate for that lack of higher order terms, and the same happens with the PDFs, in order to provide a better description of the data.
Can I ask a quick question?
Yeah.
So do you not use you only use your own determination of alpha S
No.
from those data?
That would be the pure case. I mean, I wanted to make this pure case scenario just to show the differences. We do use those results, and actually when people fit the Parton distributions and the alpha S, they include, what they usually do is include the PDC value of an extra data point, which turns out to dominate over the extraction of alpha S. And at the end, finally, it might happen that they decided to set alpha S to a particular value and do the fit already with that value. But in principle, the idea would be that one would be doing this. And in any case, the value of alpha S will be different at next to leading, next to next to leading, and so on. So even if it is an external parameter. So Parton distributions, there are, those are the guys that, those guys that provide a different set of Parton distributions are basically the ones that also provide us the value of alpha S and the masses of the quarks. Because once they have used that value of alpha S or the mass of the quark to fit the Parton distributions, we are bound to use exactly the same in terms of consistency. So, and there are analyses being done on leading, next to leading, and next to leading. I'm showing which is the state of the art, next to leading order. There are basically 6 different groups doing that. This is just a fit of the available data. They differ by the number of observables they use. 3 of them are the ones which are usually called the global analysis in the sense that they use most of the available data. Some others are more restrictive. For instance, the HERA PDF was at some point using only DIS HERA data to fit the Parton distributions and not all the other observables. And you will see that there are many differences in terms of theoretical bias, the data input, the way they treat the heavy quark treatment. But there is a large, there are large differences arising basically from the value of alpha S they use. So we have that the 3 global analyses have decided to agree on the same value in order to produce the fit. That makes it simpler to compare the results. But you can see that there are large differences in the value of alpha S being used by other groups. For instance, this group is getting alpha S only from the analysis of the Parton distributions. And that means something of the order of 4 or 5%. With this one, it's 4 or 5% of difference. When you compute, for instance, the cross-section for Higgs boson production at the LHC with these 2 extreme values of alpha S, you will find that the differences will be of the order of 15%. So it's really a serious issue, which is the value of alpha S you use for the Parton distributions. And of course, there are also very large differences in terms of the use of heavy quarks, not only of the masses, but also on whether you consider the heavy particles as massless for the Parton distributions or massive, or how you interpolate between these 2 extreme scenarios. That makes quite a large differences, particularly affecting the gluon distribution, for instance. I didn't discuss much about the masses of the quarks because we are quite behind you in that direction. Most of the analyses are being done assuming that the quarks are massless. And when we take into account massive corrections, it's usually only at the lowest order. So it doesn't make any difference where we put there the mass of the quark defining the MS-bar scheme in the pole scheme or whatever, because they will be at that order the same. So, but in principle, one would imagine that there would be extractions of the masses of the different particles. These people would be very happy to extract the masses of the particles directly from their analysis. That doesn't make sense at this point, but they could be. So just to give an idea of which is the present situation, I will show you the typical example, which is the gluon distribution at the LHC for values which are values of Q square of the other 100 CeV square, and all of them are, these results were obtained with the same value of alpha S. So what you can see here is a comparison. These guys will provide you a number of sets that will allow you to compute the central value of the cross-section, but also to estimate the uncertainties arising from the Parton distributions and from the value of alpha S. So what you can see here is a comparison of the gluon distribution normalized to one of them with the corresponding uncertainty value. And you can see that if you look at these 3 global analyses, the ones that claim to be global analyses, there is a pretty good agreement between them in the sense that there is a large overlap between the bands, but also you can see that uncertainties are of the order of a few % in the gluon distribution. On the other hand, if you include the other analyses which are not completely global, you will see that the differences are much larger. okay? And there are several reasons for that. Now, these three groups, which are the leading ones in terms of determining the Parton distributions, have decided to create a combination of them. It's called the PDF or LHC group. What they have done is to combine these three global analyses into a single combined PDF set, assuming that the value of alpha S has this central number and this uncertainty. You see it's a bit larger than the one in the PTC, just to be a bit more conservative. And what they will release, or they release, is a few hundred sets that, then, as I said, you can use to compute central values and produce uncertainty estimates. Of course, the situation is not completely settled in this direction because the other groups which are not included in these combinations do not agree with them. And actually, if you look at the literature, you will find two different recommendations from different groups. Most of the people at the LHC are using this one, but those here claim that the uncertainties claimed by this group are just too aggressive, in the sense that they should be a bit more conservative, the uncertainty should be larger. And I guess they are a bit right. I would say that the truth is somewhere in the middle, probably more in this direction. But the results presented here are a bit too optimistic in the sense of uncertainties, and actually that is being confirmed by the fact that the same groups are doing now new sets, new analysis with the new LHC data, and they are finding now differences which are larger than the one they previously assumed. So it might happen that in the next few years you will see that the uncertainties coming from Parton distributions in different observables will be larger than the ones people were claiming so far. Okay, so that was about the Parton distributions. Let me concentrate on the perturbative part. Over the last 20 years, there has been an amazing progress on the field in order to include electroweak corrections, matching with Parton showers, adding resummation on top of many observables in different ways, and particularly about automation of the calculation of higher order corrections. But I would like to concentrate on the core of any calculation. We know that the core of any calculation is a fixed order result, and on top of that, then we will include all the improvements. So I will try to give an idea of which is the present situation in terms of from leading order up to n-cube calculations for different observables. I don't need to tell you that we know how to do a Born level calculation. That's not very difficult. And actually, with modern techniques, it is possible to compute now the cross-section for the production of, say, 20 sheds at the LHC without much problem, okay? Which was numerically impossible a few years ago. It's a Born level, simple to compute. It's very simple to integrate this calculation to Parton showers, but we know that for the LHC, leading order is not enough for precision physics. I would say today leading order is not even enough for a qualitative approach to any observable. Everything that we do today starts at least with an next to leading order calculation. And the reason why, well, I don't need to go too much in detail about where we need higher order corrections, but let me give you a couple of examples. One particular example which shows that we really need to include higher order corrections actually to rather high orders is the fact that the conversions of the QCD expansion is usually rather slow. Alpha S is a large value, so you need several terms in order to get enough precision, particularly if you want to reach the percent level. But one particular perverse case is Higgs production. If you look at Higgs production, which is dominated by a gluon-gluon into a heavy quark loop that then produces the Higgs, you can see how bad the conversion of expansion is if you use the typical renormalization and factorization scales as the mass of the Higgs. If you pull out the Born level cross-section for the inclusive result, of course, at leading order, you get a 1. At next to leading order, you get a 90% correction. Next to leading order, 55% correction. N-cube below, 30% correction. So it's really slow conversions in order to provide reasonable results. So it's not an academic issue only, go to higher order corrections, but I don't need to convince you about that. It's also from the point of view of phenomenology or experimental approach, very interesting to go to higher order because the higher is the order, the more particles you will have in the final state, and then you will be able to produce a better matching between the theoretical calculation and experimental conditions, particularly if you look at sheds, for instance, or transfer momentum of different particles. Of course, you know about that very well. Apart from having precise central values, we want to have some estimate of the theoretical uncertainty, and typically what we do is, as you do, variations of the factorization and renormalization scale by a factor of 2 up and down with respect to the central value. The factor of 2 is just for historical reasons. It doesn't need to work really, and you will see examples where it doesn't work. Well, for instance, this is the Drell-Young cross-section. You see that the leading order calculation, even if you perform this variation, does not overlap with the next to leading order result, which means that at leading order, doing a change of scales, variation of scales by a factor of 2, is not a good estimate of the higher order, missing higher orders. But when we go from next to leading to NNLO, you see that there is a very nice conversions. There is a complete overlap, and also there is a substantial reduction on the what you would call the uncertainty estimate. So certainly a good idea to go beyond leading order and higher orders. And I will skip that, but there is also some cases in which you really need to go to higher orders because it's only at higher orders that you open new channels that in principle are suppressed by powers of alpha S, but might be enhanced by large gluon luminosities at the LHC. So this is one case. For instance, diphoton production, which starts at QQ bar, has a correction at order alpha S squared, which is this box contribution, gluon into two photons, which is suppressed by 2 powers of alpha S, but is completely enhanced by the gluon luminosity, which makes this contribution as large as the leading order one. So it's only typically at next to leading order, you have all the channels for your process open, and then your calculation becomes more sensible. Now the reason why we can do many next to leading order calculations is there was a big revolution over the last decade. If you look at the pace of calculation at next to leading order, and in hadronic collider, if you want, it was taking about 10 years to add one extra particle in the final state. So there was Drell-Young calculation in 1980, 2-shed calculation 10 years later, 3-shed calculation 10 years later, 4-shed calculation 10 years later. So it was really slow, but there was a revolution over the last, in the last decade, and that revolution came from the calculation of one-loop amplitudes. The real bottleneck was on computing the virtual contribution, even though we know from the technical point of view how to do that at one loop, just do Passarino-Bellman, and then you compute your amplitudes. It turns out that when you have many particles in the final state, large multiplicities, that is numerically impossible at some point, and that was restricting our ability to compute higher order corrections. There were many improvements over the last years, either coming from people doing the traditional Feynmanian approach or the Unitarian approach, everything condimented by revolution, understanding that this Passarino-Bellman decomposition that one uses to do at the integral level can be done at the integrand level also, and then basically today computing a one-loop amplitude is just solving an algebraic problem that can be solved numerically, and then you can automatize it. And you can automatize it so well that we are reaching the final goal for this field, which is next to in order automatic calculations, which means zero cost for humans, really zero cost for humans. The problem is basically conceptually solving, though there are still some technical issues. But in a few years, we have already seen the appearance of a number of codes that allow to compute the next to leading order cross-section in an automatic way. By automatic way, I mean this. How difficult it is to do a next to leading order calculation these days. For instance, if you want to compute proton-proton into TT bar plus jet, not only the total cross-section, but also distributions, you download this code, MATGraph 5, you run these 6 commands in your terminal that will produce another code that we will run at the end, and that will compute your cross-section. It will take about 5 minutes to generate this code. It takes about 30 minutes in a 20-core machine, not even a cluster, I would say, to compute the cross-section and the distributions. And actually, you can find in this particular paper that they computed something of the order of 150 different observables at next to leading order, just in a pure automatic way. So it's a really impressive achievement. There are still limitations. If you want to compute observables with very high multiplicities, too many particles in the final state, for instance, if you want to compute 5-shed production at the LHC, this program will run, will generate you a program, you will run it, but the numerical conversions of the result will be so bad that we'll not be able to get any sensible physical result from there. So we still need there, for say, 5 or more particles in the final state, still some manual work, and this is one particular example of people that had computed 5-shed production at the LHC, showing actually that not only that it was possible, but that phenomenologically the next to leading order corrections turn out to provide a better description of the experimental data. Okay, not everything was solved, but there is constant progress. this code, MATGraph, not only computes the cross-section at next to leading order, it would also provide you the proper matching with the Parton shower at next to leading order accuracy, so you will get results that you can directly compare to experimental data. There is a lot of work in order to include QED and electroweak corrections also in an automatic way. The most difficulty appears with processes which are loop-induced, processes like, for instance, gluon-gluon into two gauge bosons that are one loop already at the leading order and then going to next to leading order means computing two loop amplitudes that are much more complicated. But people are including now BSM in these codes in such a way that you just type your Lagrangian and that will provide you the next to leading order cross-section for the process you are interested in, and particularly higher dimensional operators. So everything is automated and it's quite impressive. So after solving basically the next to leading order problem, people move into the next step, which is next to leading order, and we also have seen a revolution, I would say, since 2014. You can see that a number of different processes that were computed at this accuracy. Of course, the calculations here are much more complicated. On one hand, you have to deal with two loop amplitudes, which are very difficult. On the other hand, you have to deal with the double real emission, means two extra particles that produce a lot of infrared singularities, and we still don't have a fully developed method that can be automatized in order to deal with these divergences for any process. So what we have are different approaches that allow to compute different observables, but nothing can become completely automatic so far. So I will give you just one example to give an idea of the difficulty in order to reach this result. Die shed production at the LHC, this is a very important process for many reasons, particularly if you want to fit Parton distributions. This is a calculation that took 20 years to reach it. People computed the two loop amplitudes in 2001, and they still haven't finished in the sense that this group has produced results at next to leading order accuracy, but using only the leading color amplitudes. So we still need some work in order to include the full amplitudes to next to leading order accuracy. And just to give an example of the relevance, you can see here the comparison for die shed production. Let's see, for instance, at small invariant masses and central rapidities. You see the blue line is the next to leading order, or the blue band is the next to leading order expectation. The NNLO is the red. You see that the corrections are small, but they are in some regions outside of the next to leading order uncertainty band, and particularly that they provide an excellent description of the experimental data when these corrections are included. So it's a beautiful piece of work that phenomenologically turns out to be quite relevant. So the new frontier is now NQ below, and actually if you want to reach this 1 or 2% accuracy that is claimed that we will need in the next 20 years, that's in the direction we have to move. As you can see, there are first calculations started just a few years ago, and they are related to very simple observables. That means Higgs cross-section or Drell-Yang. So the production of one single colorless particle in the final state. That's all what we can do at the moment. So that's one example, Higgs at NQ below. So this is the Higgs cross-section in terms of the renormalization scale, factorization scale, leading order, next to leading, next to leading, and NQ below. So you can see that only when you reach NQ below is that you really get a cross-section which is pretty much flat in terms of the variations of the scales. And by comparing to the previous orders and by choosing properly the renormalization scale, which is here typically the mass of the Higgs over 2, we can claim that today we have a perturbative uncertainty in this observable which is of the order of 2 or 3%. So at that point we have reached that goal. Actually, there are other uncertainties in the Higgs cross-section which are larger than the perturbative ones so far. But not everything is so nice. There is a very recent calculation, still unpublished, and you will see why it's still unpublished. It was presented in a couple of conferences. It's Drell-Yang production. You imagine that Drell-Yang is the simplest, most beautiful process that should show great conversions and everything should work fine. It doesn't, actually. So what you can see here is the result of the computation up to NQ below. Everything is normalized to NQ below. So this is the leading order band. Nobody cares about leading order. It's far away from the rest, not the problem. Next to leading order, the yellow, the blue is NNLO. So you see that the band is well inside the previous band, estimated again by performing scale variations. And there is a considerable reduction on the size. But when you go to NQ below, you see that the band is of the same size of an NLO, and that there is no overlap between them for certain values of the invariant mass of the photon here. So that's an issue that people are still trying to understand, which is the origin. Of course, there could be different reasons. One of them is that we are pretty lousy at estimating uncertainties. That game of playing a factor of 2 up and down with the scales is something that was maybe reasonable when we were doing leading or next to in order calculations, but now it's completely not enough in order to reach the precision we want to reach. And really, we have to come out with a different approach in order to estimate uncertainties. And there are not many people working on that, so that's an issue. The other problem, of course, is that this is NQLO calculation, but there are still no NQLO PDF, so it might be that NQLO PDF will actually help to solve this gap between these two terms. And we will see that soon because there are people already computing the NQLO splitting functions, and I guess it will be ready in a couple of years. So I get to the conclusions. There has been an amazing progress in fixed order calculations during the last 1 or 2 decades. That means we have reached automation at next to in order. Many processes at NNLO, particularly those which involve 2-to-2 processes. We are reaching NQLO for simple kinematics and the first set of splitting functions. Automated effects for QED, electroweak, BSM, effective field theory, Lagrangians. But we are reaching new bottlenecks. As I said, large multiplicity at next to in order still needs manual work. The loop-induced processes, particularly if they are massive, they are hard to tackle. NNLO is very difficult for more than 2 particles in the final state. Going to 3 particles here will be very complicated. Now people are starting to compute the virtual amplitudes. In the massless case, in the massive case, of course, they will be really complicated. But also the real radiation will not be trivial. The treatment of the numerical infrared divergences will be complicated. So we will need significant development over the next few years in order to reach this percent accuracy for some other processes. And certainly, I would like to insist that we need a more rigorous treatment of theoretical uncertainties. This simple variation of the scales, a factor of 2 up and down, is not enough for the level of precision we are reaching today. So thank you for the attention.
Are there questions? Or
so you mentioned that likely the uncertainties in the PDFs are underestimated. If that is corrected for, does that mean that the extraction of the weak mixing angle and the W mass and to some extent the top quark mass, their PDF error will all have to be increased?
Yeah, I guess so. I mean, we will have to wait a few more months until all these groups come out with a new set of Parton distributions. But everything points out into the direction that the uncertainties will increase, and they will affect the extraction of those observables. I don't think too much. How much is the PDF uncertainty?
Well, for the W mass, it's about 7 MeV out of 12 MeV for the world average. So it's the dominant error in a way.
Okay, okay.
Danny, so about this mismatch that in this community here, we normally determine alpha S using all the information available, which means in many cases now N4LO and 3LO and so on. Would you think it would be interesting if we would also extract alpha S coherently order by order, as you mentioned? So do NLO and then leading order, next leading order and so on, extracting errors? Because it's true that we never did, I certainly never did that in any of the determinations we did.
I think it would be interesting in terms of having a better comparison between what is done in one community and the other. Because we see now these tables of extraction of alpha S from many different observables. They have a lot of different theoretical biases included into that, and then comparing them is not easy sometimes. And I think it would be useful. I don't mean that this is the value of alpha S you should use. I understand completely that there is one value of alpha S that you're trying to find. But for us, since we use it in a more effective way, it would be, I think it would be easy. It would be a good idea, yeah.
So when you say that you need to use the lower order alpha S when you are having a lower order expression, I mean, as I see it, I think what's very important is that you use the same alpha S in your PDF as in your Partonic, because you want to cancel the factor.
Absolutely, that's for sure. Yes.
Because the mu f, right, has to cancel and it will on because the PDF will evolve and then your matrix element will. It has to be the same alpha, otherwise you're screwed.
Yes.
Would you agree on that?
I agree. I fully agree. And I'm not claiming that what we are doing is perfectly fine. It's partially a convention, but it's a convention everyone uses. And if the PDF do the analysis with some particular value of alpha s, we are bound to that, yeah. Well, the situation is a bit better because, as I said, they produce hundreds of sets, and some of these hundreds of sets correspond to different values of alpha s. So somehow you have now the possibility to choose a different PDF which has a value of alpha s you prefer, but yeah.
So I have a comment about mass schemes. You mentioned that briefly, and I think these days this is becoming ever more important because we're doing Higgs physics, and there, of course, mass effects are very important.
Yes.
See top-bottom interference like that, and we will have to be careful with the mass schemes, especially considering that with these massive quarks, calculating higher orders is very difficult. So.
I completely agree.
Something that
let me see if I have it
has
here.
to be thought about.
Maybe I can show one particular extreme case for what you are saying. I had it somewhere. Oh, I deleted that. Oh no. Well, anyway, the point is that one particular case where you see this effect is if you look at double Higgs production. Double Higgs production goes mostly through this process. So it actually makes a big difference, not only which is the value of the mass at the top, but which is the scheme you use to define the mass at the top. And people have found that even at next to Lean order, which is the highest order which we have computed by including the value of the mass of the top, exactly, there are differences of the order of 20% in the cross-section if you move from mass of the top in the MS bar scheme, or you go into the pole mass, or you change the scales for the MS bar scheme. So it's a real issue, and we don't know how to solve it. Because one possibility, of course, is to go to higher orders, but one order higher than that with a heavy particle in the loop is very complicated. Actually, this result was obtained only numerically, not even analytically. Or the other is to try to perform resummation for these effects, but nobody knows exactly how to do it yet. You're absolutely right.
So you commented that one should do better than, with estimating uncertainties than just varying the scale by a factor 2 up and down. So what should one do instead?
As far as I know, there is only one group that has been doing that, and not many people pay much attention. It's this group from Paris that they have tried a very simple approach, which is the following. We have many observables computed at next to leading order and at next to leading order. So we can try now to check numerically which is the variation of the scales we have to do at next to leading order to reach the NNLO result. And what typically find is that what you need is, this coefficient R, that if you want to reach something like 68% of the observables computed at next to leading order matching the NNLO result, you need to change the scales by a factor of 4 instead of a factor of 2. So, of course, if you go to the next order, probably you don't need such high variation because the perturbative contribution will be smaller. But there have been some attempts to do this in a more statistically sounded way, but people are not paying much attention. And I think the reason is that if it takes 20 years to compute your cross-section, you don't want to spend one extra week even in, in looking at the uncertainty. But we really have to do it now. We really need a group of the community discussing these issues and finding a more reasonable approach.
Following up on that, I mean, sometimes it's not how much you have to vary. You need also a very good guess for your central scale.
Of course.
Right, and then if you find, I mean, first you have to figure out if there are other scales, like there's a soft scale you didn't realize, then you're screwed. Mm-hmm. But say that you have everything under control.
Absolutely.
I mean, finding the central scale and then you vary up and down.
Of course.
It's crucial. I mean, sometimes it's also these logs of pi, not logs of pi, the pi's.
No, the problem is that when you look at high multiplicity processes, you have many scales, and it's very difficult to choose one which is the average and it's not very far from the others. And then you turn out introducing large logs explicitly by choosing one particular scale or the other. So, but even the change of the scale is not completely meaningful, no? In the sense that the only thing we can estimate by changing scales is our terms that come up from the normalization group variations, but there could be other factors like pi squares, constants, or whatever that we are not be able to guess from these simple variations. So, yeah.
Are there other questions? If not, let's thank Dan again. And we have a coffee break now. 20